Hello and welcome back to another Kingdom Math Guy video. And today we'll be doing something special. Today we're gonna prove the AMGM inequality. So, well, for all cases actually. So let's first take a look at what AMGM actually is. What does it say, rather? So for any positive integers a, b, well, not positive integers actually, positive real numbers greater than equal to 0, right? We have that a plus b over 2 is greater than equal to the square roots of ab. Yep. And that's what the theorem says for the case of n equal to 2. The name AM stands for arithmetic mean, which is the average that you usually do it. And then GM is the geometric mean, which is the square roots, well, it's the nth roots of the product of n numbers, which is also a form of average, a form of mean actually. And this is the case for n equal to 2. We're gonna prove the case for n for every single, well, actually for all n greater than equal to 2. But first, we'll prove it for the case of n equal to 2. Let's start. We'll actually present three methods of proving this. Let's start with method 1. All right. So we need a prerequisite. So this is the trivial inequality. Inequality. It takes quite a bit to write inequality. That is x squared is greater than equal to 0. And this inequality is pretty basic, right? It's pretty intuitive as well. But like for a formal proof of this inequality, I recommend a video by the channel Iliekmathphysics. He has some really awesome stuff on proofs, and I recommend you check that out. I will put a link in the description, so you may check it out. Anyway, with this trivial inequality, we can start by our first method. Yeah, so using the trivial inequality, we can plug in a minus b into the trivial inequality, and we get a minus b squared is greater than equal to 0. Right, and then this thing, we can use the binomial extension to figure out that this thing is actually equal to b squared, or is equal to this expansion. And then we know that this expansion is still greater than 0 because these two are equivalents. So we can add 4ab to both sides. So we get a squared plus 2ab plus b squared is bigger than equal to 4ab. And then we can, this thing we can group into a plus b squared, which meaning that it has to be greater than 4ab, and then we have that a plus b is greater than equal to 2 square roots of ab, and then we can divide both sides, and then we get, well, the desired results. Okay, so this is one way of proving it. Yeah, let me clean the screen and then we'll proceed on to the next one. For the second way of proving it, we will again use the trivial inequality. But instead of a minus b, we'll plug in rad a, the square root of a minus the square root of b. Right, and then if we square this thing, we do get, well, this thing has to be bigger than 0. And then this thing is a minus 2 rad ab plus b, right? And then this thing is greater than 0, and then we can just group it together, get that this thing is bigger than 2 rad ab. And then, well, again, we get the result is greater than rad ab. And then we have a final and third way. Let me clear the board again, and then we will show it. The third way is a little bit more geometric. It's a more geometric argument. So suppose we have a line segment, and then we have, let's say here, this is A and this is B. Then we draw a semicircle around it. Okay, so we can, first of all, we can, from this point, well, I guess the point of intersection, I guess. No, it's not really, anyway, just like the segment that cuts into A and B, right? We can drop a perpendicular down to this point, and then we can then connect this to the edge here and then the edge here. Right, the line is not that good. Forgive me. But anyway, this thing by Falley's theorem, it's a right triangle. And then this thing is also a right triangle by the fact that it's a perpendicular drop onto that. And this thing has side length b, and then let's call this thing h. So we notice that there is actually quite a bit of similarity here. So for example, this angle uh, and this angle, they are complementary, right? Since they have a right angle here, and then these two must be complementary. And since those are complementary, notice that this is 90 minus this double angle. Well, two tick is 90 minus this angle, and then this is also a right angle, so this is also 90 degrees. And then by the I think it's the line partition segment, the theorem. We get that this part must also be one tick. Then this part must be also two tick. Then we can use some trigonometric function or just similarity to get some relationship. Namely, if we do tangent of one tick here, it's gonna be uh, this thing is gonna be h over a. All right, and then if we do tangent, oh actually, I made a mistake. Sorry, this should be one tick. Right, my apologies. And then this thing is gonna be again a one tick. This thing is gonna be h over b. Right? Since they're equal to each other, we can set it. Well, actually, this thing is opposite of chase. Oh, my god. Okay, sorry. Alright, this is quite bad. This is a one tick, and then this is a two tick, right? Yeah, and then okay, that just shows you that like mistakes happen. All right. So this is the one tick. The opposite over. So the tangent of this one tick is equal to b over h. Right. We can set the ratios equal to each other, so we get b over h is equal to h over a, and then we get a ba is equal to h squared, and then the height is equal to square roots of ab, and then so this thing is rad ab, right? And then this thing, what we're gonna do now is that we suppose that this is the center, right? And then it's the center of the semicircle. Then we can draw another line from that to that, and then well, okay, this is terrible pick. Let's just say okay, it's clearly not drawn to scale, but let's just say this is the center, right? And then this argument will work regardless of scale. So yeah, and then we notice that this from this to this is clearly the radius, right? But what is the radius? The radius is diameter is half the diameter. Now notice that the diameter is a plus b, so the radius is going to be a plus b over 2. But what do we know about the radius? This thing is actually the hypotenuse of this right triangle. And then what do we know about hypotenuse and the legs? Well, we know that the hypotenuse is always bigger than one of the legs, at least its legs, rather. Again, we prove this again with a geometric argument. Yeah. Anyway, now that we have proven the AMGM inequality for n equal to 2 for the case n equal to 2 for in three different ways, we can now proceed to actually generalize this theorem. And we can start by proving the case not for n equals 3, but rather for n equal to 4. All right, let's see what happens when we try to prove this. Or rather, how can we prove this? So the theorem says that a well let's write a plus b plus c plus d. All right, and then let's divide this thing by 4. And then the theorem says that this thing is bigger than the cube, or at least the cube roots of a b c d. Right, and then what's but we don't really want to have this here because usually for a proof you just want to go from here and then try to show that it goes here rather than like having it set as a goal that you reach. You just I guess it's you don't want to just have it there. You just want to reach it as a result, not as like a direction to go to. Anyway, this thing a plus b plus c plus d over 4 want to prove that it is satisfying the inequality. And then what we can do to prove this is that actually we can use the n equal to 2 case. How do we do that? We can write the fraction as a plus b over 2 plus c plus d over 2, right? All over 2, right? And then what do we know about this? This looks like AMGM, right? But a is a plus b over 2, and then b is c plus d over 2, if that makes sense. So we can apply the AMGM, and then we know that this thing is bigger than the square roots of a plus b over 2 times c plus d over 2, right? And then, but this doesn't look quite like what we wanted, right? But we can still keep simplifying this. We know that this thing is at least, by the AMGM again, we can apply it onto this. We get that this thing is at least square roots of AB times the square roots of CD. And then we know that this thing, we can just make it a double square roots of ABCD. And then we can realize that this thing is just the fourth roots of ABCD. Right, so we have proven this result because this is a chain of, well, greater than equal to sign. So yeah, we prove this result for n equal to 4. Now the next one we're gonna do is not n equal to 5, but actually n equal to 8. So for n equal to 8, we do the same argument, right? Well, actually, I don't really, yeah, but anyway, let's just write out all the 8 terms: a plus b plus c plus d plus e plus f plus c d e f g plus h. Well, usually you actually write this as a1, a2, a3, a4, all the way to a8, and then over 8. Now this says that this thing should be greater than the eighth roots of a, b, c, d, e, f, g, h. Again, we don't want to have the result here because a proof shouldn't, depend on the result. Anyway, this thing we can prove again using the theorem that we just proved, which is AMGM for the case of 4. Right, so we can rewrite this fraction as a plus b plus d over 4 plus a well, e plus f plus g plus h over 4, and then all over 2. And then this thing we know that this thing is greater than equal to the square roots of, yeah, it's gonna be kind of messy to write out. Well, not plus, but rather multiply by e plus f plus g plus h over 4. And then we can use the AMGM for case n equal to 4 again. So we get that this thing is the fourth roots, is at least the fourth roots of a, b, c, d times the fourth roots of e, f, g, h. And then this thing, we can combine it. We get the square roots of the fourth roots of a, b, c, d, e, f, g, h. And then this thing, if we could just combine the, I guess the roots, you get the eighth roots of a, b, c, d, e, f, g, h. And then this thing is all under the proof. All right, nice. But now the issue is if we want to prove it for more cases, we will have to do, infinitely many cases. And well, we realize that this definitely works for any n equals to 2 to the k, right? That is, and that is a power of 2, right? And then, so this thing, since it works for, we can presume that it works for all powers of 2. We will use something called a Cauchy induction to prove that it works for all powers of 2, right? So we know that it works for 2, which is 2 to the first, as we have proven it in 3 separate ways. And if we assume that 2 to the k works, right? So it works for 2 to the k. Then we want to prove that if it works for 2 to the k, then it must work for 2 to the k plus 1. And then we basically did this already, right? This argument is, we can reiterate it. Basically, every single time we can write the fraction or a1 plus a2 plus dot 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 all the way to a to the 2 to the k plus 1 as something like, no, this fraction is going to be 2 to the k plus 1, as something like a1 plus a2 plus dot dot dot, and then plus this thing is going to be divided by actually I guess I should bound this thing. This is going to be 2 to the k. I divided by 2 to the k plus this thing is going to be a to the 2 to the k plus 1 plus dot 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 all the way to a to the 2 to the k plus 1 on top, right? And then this is 2 to the k, and then we can divide all that by 2. And then since we know that the theorem is true for 2 to the k plus 1, we can reiterate the same argument. And then we get basically the same result as we've done before. I will not show the proof explicitly because it takes quite a bit of space, and I don't really want to write all over this dainty little whiteboard. So yeah, it's a good exercise to try it on your own. Yep. But we will now go into actually proving this for every single n, and not just powers of twos. So the way that we do this is that we first start off by saying that every positive integer, k, has to be between 2 to the n for some n. Well, if k is not a power of 2, then it is between 2 to the n and 2 to the n plus 1. Now we take this as a given, but to prove this, it shouldn't be that bad to prove this. I think you can use induction actually. Yeah. And then since we know that k has to be between 2 to the n and 2 to the n plus 1, so let's write k as 2 to the n plus some j, right? So we want to prove this, that AMGM works for the case of k, which is 2 to the n plus j, right? So first we'll write out the fraction a1 plus a2 plus dot 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 all the way to a sub k over k, right? And then we want to, well, let's note that this thing is not that nice, right? Because this thing is not a power of 2, and this thing is not a power of 2. It's just impossible for us to get to a power of 2, like, no matter how hard we try with this, right? But then a neat trick that we can do is that we realize that this thing is just equal to the average of this list of numbers. And then what do we know about the average? Well, the average is has an interesting property. It's if you have, let's say, a plus b over 2 is equal to m, right? Then a plus b plus m over 3 is also equal to m, right? So now this is really nice because we can now rewrite this expression as a1 plus a2 plus dot 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 ak plus, and then we want to do 2 to the n plus 1 minus 2 to the n, which is 2 to the n minus j. So plus, we keep going dot dot dot. Well, actually, we don't need to dot dot dot. We can just say it's 2 to the n minus j times m, right? Because we're adding that many m's, and then we are getting 2 to the n plus 1. So now what's nice is that we know that we have proven the AMGM for 2 to the n for any n. Then it must be proven for n plus 1 as well. So since that is the case, we can now say that for sure this thing is greater than 2 to the n plus 1, right? And then this thing is going to be a1, a2, dot dot dot, ak times m to the 2 to the m minus j, right? And then this thing is pretty nice because this thing is, well, this thing here is equal to m actually. So this thing here, so that is saying that m is greater than this thing, right? So since m is greater than this thing, we can take the, let's write this a little bit better. We can take the two, yeah, wait, two to the, okay, this is really terrible. But anyway, we can take it to 2 to the m plus j roots on this. Actually, no, 2 to the m plus 1 roots on this. I mean, the power on this. And then we have, this is a1, a2, dot, 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 ak, m to the 2 to the n minus j, right? And then we can multiply, well, we can divide both sides by this, by m. And then we do get the m to the, this thing is going to be 2 to the n plus j, which is just equal to k is greater than the, greater than a1, a2, dot, 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 ak, right? But then this thing we can take the 2 to the n plus, plus j roots on both sides, and we get m is bigger than equal to the 2 to the, okay, this is getting really bad. Let me actually clean the board. Sorry about that. So in the end, we're gonna get that. Okay, we're gonna get that. Okay, why is this there? Anyway, we're gonna get that m, which is equal to the original average, a plus a1, a1 plus a2 plus a3 plus dot 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 plus ak over k. This thing is bigger than equal to 2 to the, well, this is just k actually, k roots of a1, a2, a3, dot dot dot, all the way to k. And thus, this is the theorem that we'd like to prove, and then we can conclude that this is done. Yeah, so that's pretty nice. We proved AMGM. And then for future videos, I might show a few examples of how we can use AMGM to solve some problems. Also, we might talk about the weighted AMGM inequality, which is basically a corollary to the AMGM by having multiple terms be equal, which is giving them quote unquote weight. It's also an interesting thing to do, yeah. But let's give the viewers some exercise for fun. So I want you to find the minimum value of the function y equal to 2 over x plus 3x for all x greater than 0, right? This thing you can use AMGM, right? You can use calculus if you know how to use calculus, and you can use graphing if you know how to use graphing. But I want to see you do it with AMGM. So if you find a solution, please post it in the comment section. I hope you enjoyed this video, and I will see you in the next one.